Welcome to Forces and the Laws of Motion, Chapter 4. When school broke up as COVID-19 hit, we were in Forces and we were actually doing a modeling unit, Unit 4, and we were about ready to transition into Unit 5. So, rather difficult at the moment to get into those units in the spirit of how they're supposed to be deployed, and I'm working on a way to figure out if we can do modeling from a distance together. But until then, I do have some previous presentations when I just taught strictly out of the book, and for the meantime, I will use those, I will repurpose them, modify them, and make them a little bit more friendly for online presentation. But this is going to correspond then with Chapter 4, Forces and the Laws of Motion, which is really a combination of Unit 4 and 5 in the modeling units. So it does, in many respects, cover all of that. Okay, here we go. I do recommend that you take notes, and that you certainly, because this is a video as opposed to a slideshow, I've actually videoed it, that the slides will change on their own. It'll go all the way through with the narration that I offer. By all means, please pause, stop, slow down, rewind, fast forward, whatever you need to do. Take notes along the way. I highly encourage you, because this is now coming out of Chapter 4, I encourage you to read the chapter like you would in a typical classroom. But along with that, if you do want to take notes and work through, kind of a slower pace, then watch it once all the way through, and then when you go back, maybe turn the animation off and pause, write down a slide, skip to the next, etc. So that's what I would recommend to you. Okay, here we are, Forces and the Laws of Motion, Chapter 4. In Chapter 4, Section 1, here are your objectives. You can read those objectives, and you should be able to accomplish all of that by the time you read the section, look over any homework that is deployed for the section, and the notes, of course, that we are in the presentation that we're talking about right now. Okay, what is a force? Well, we've already talked about this. It's a push or it's a pull that's exerted on some sort of an object. Forces can cause change in velocities. That's what they do. And you can see the various conditions and the various different let's see, what do I want to call this? I'm trying to activate the laser pointer, so I'm distracted. I'm sorry. These various aspects to what a force can do. So it can cause an object to go from rest to have a velocity. It can cause something to accelerate or decelerate, simply a change in velocity, so you have a different initial and final values. You can go from velocity to rest. You can stop something, or you can change the direction, and some of this can happen at the same time. Change direction and speed up, change direction and slow down, or stop, etc. What are the units for forces? Well, we already know that they're newtons, named after Sir Isaac Newton, but it is a derived unit of measurement. It is a derived unit of measurement that comes from the combination, rather the product of, to be mathematically correct, the product of a mass in kilograms multiplied by an acceleration in meters per second for every second, or meters per second squared. When you multiply those values together, the units combine into a kilogram meter per second squared, and that then simplifies to a Newton. That's where a Newton comes from. We know, of course, that there are various types of forces. There are 4 known field forces that exist in nature, in the universe, and then everything else is a contact force, meaning that contact must be between the two objects in order for the force to be experienced. As opposed to a field force, no contact is necessary, such as gravity. Gravity can attract without being in contact with something, and I think we're familiar with that. The other forces that are field forces, electromagnetism, 2 nuclear forces, the strong and the weak, are also field forces. We've already talked about force diagrams, often called free body diagrams, although technically they are different. A force diagram may have actually all forces at work. So you see this car hitting a brick wall or touching a brick wall maybe, and we see forces at work in the brick wall and in the car between them. As opposed to if we're just isolating the car as our system, what we're going to study, then we only look at the forces acting on the car itself. So that's where a force diagram and a free body diagram actually differ, because it focuses on the body or the object that you're looking at. However, I use these terms interchangeably, and I know a lot of people, a lot of educators, a lot of students who do. I rarely, if ever, need an actual force diagram for anything where all the forces are being shown, even something that's not necessarily in our system. And so most of the time I'm looking for free body when I'm asking force diagram. So if you're ever worried, by all means please clarify. And if you get to college and you take college physics, you will certainly want to clarify with your professor what they mean when they indicate force diagram, free body diagram. Okay, this is just examples of force diagrams, free body diagrams. We've seen these before, so I'm going to move on. You can certainly pause and look over the slide more carefully. Here is a car being towed, I guess, and we have some values. So tow truck expertly applies 5,800 newtons at 10 degrees. Gravity is going to exert some forces. The road's going to push up with its own force, supporting force, the normal force of that value there, the 13,000 value. And we have some friction on the tires as the vehicle is towed down the road. So if we want to then assign values for everything, we have, of course, our car here right in the middle, and then in a sequential step-by-step diagram, then we see the car, we see then the what's going to be the towing force from the cable, most likely described as maybe a tension force. We have the force of gravity down, we have the normal force up, and we have certainly then included in this last diagram friction. Now, of course, the normal force and the force of gravity are not equal to each other, even though the object is not flying up or crashing down through the ground. But remember that the tow truck is also lifting up. And because it's on an angle, part of this 5,800 newtons is going to complement and add to the normal force, which would then exactly counteract the 14,700. And so those forces up and down would be equal. And if it's not accelerating, by the way, then the forward force will equal 775 newtons, because the backwards frictional force is that if it's not accelerating, then all forces could technically cancel out. Which brings us to net external forces. So when all forces do not cancel out, there is what we call a net force. And this means that not everything does cancel. If not everything cancels, whether it's horizontally or vertically, then there will be a change in the motion, whether it's speeding up, slowing down. It could be a change in direction. And so that's a net force, and what the result of a net force actually is. So net forces cause change in direction and motion. When all forces cancel, there is no net force, so net force equals 0, sometimes F sub net, so F net equals 0. Therefore, the motion remains unchanged. It can be constant, it can be motionless, but it will remain unchanged if the net forces are 0. Okay, in section 2, that's all of section 1 right there. It just kind of sets everything up. So with section 2, here are your objectives in section 2. And if you remember back in chemistry or possibly Science 9, whenever I present book objectives in a presentation, they're always really good they're good places for me to mine questions for a test. And so I always encourage people to interact with the objectives, whether it's mentally thinking about the answer or actually physically write them down. But these make very good test questions. What I will say, though, is I normally don't pause too long on objectives unless I see a star or an asterisk out here somewhere. If I see a star or an asterisk, that tells me that that objective is either heavily modified from the book enough to where I need you to write it down or at least acknowledge it, or it's a brand new objective that's not in your book but I feel is relevant to the material at that time. I do not see anything here, so other than the explanation of objectives themselves, I would actually just fly through this slide very quickly, because you can read it, you can write it down, you can get it out of your book. Okay, so section 2 starts to go into laws of motion, and this really comes all the way back from the 1600s and Isaac Newton and his discovery of how motion works. So Newton's first law, actually, it's numbered, number 1, first law, is the law of inertia. Basically, it's It's a resistance to motion, if you will, or as on this slide, the tendency of an object not to accelerate. So it's a resistance in motion. Newton's first law reads something like this. Depending on who you talk to and what book you read, it'll read slightly differently, but here's this one. An object at rest remains at rest, and an object in motion continues in that motion at a constant velocity, in a straight line, by the way, unless the object experiences a net external force. That would be an unbalancing force, and an unbalancing force can cause the object to change. So it would not stay at rest, or it could come to rest. It would not stay at constant velocity, it would speed up or it would slow down, or it would change direction. So that's what a net force can do once applied to the object itself. When all forces don't cancel, a net external force is present, and motion will change. Okay, determining net external force. So here I have an example of a book sitting on a drafting table, say down in Mr. B. Boyer's room. Drafting tables often are at an angle to make a drawing, if you're manually doing something like that, much easier than if it's flat. So we have a book on a drafting table, 35-degree incline, 11 newtons of friction up the table, 18 newtons of friction from the table itself, 22 newtons of gravitational force holding the book onto the table, and the question here is to determine the net force. Now, if I did my homework correctly, the next slide should have some sort of an answer to this. And fortunately, I remembered to include it, so wonderful. Well, over here on the left-hand side, because your book makes no mention of this, it's kind of purely a modeling community thing for physics, is a system schema where I have my book, which is the system, so I put a dotted line around it, and the table, which is interacting with the book, and the earth, which is interacting with the book. The table is in contact with the book, providing the book support and also friction, and then the earth is pulling on the book as well, acting on the book. So here I have my 35-degree angle with the respect to the horizontal. This is the table. Here's the book. I did my force diagram superimposed right onto the book itself. So of course I have the normal force due to the table, so table on book up, perpendicular to the table. I have then the force of the earth acting on the book, and that's always perpendicular to the earth, so that's why it's on angle with the table. And friction, which is resisting the book wanting to slide down the table. Friction is acting up the table. Now we know already that we want to oftentimes investigate components. And so we have part of gravity pulling the book down, or attempting to pull the book down the ramp or the table. And we have also a component of gravity that is holding the book to the table, counteracting the normal force up here, the table on the book. So I went ahead in blue and I've drawn the component forces. This angle here, the 35 degrees, is imposed over here, law of triangles. If you just orient it over its geometry, that's the same angle. And so this is the force of gravity acting in the y direction, and so I've used that y subscript as well, and this is the force of gravity acting in the x. And that's what's pulling it down the table. This is what's holding it to the table. So once I determine these components, I can ignore gravity itself because it's not really going to help me out with the rest of this. So if I wanted to calculate the force of gravity that is holding the book to the table, so that's force of gravity in the y direction, it's going to be a cosine function because this is an adjacent side to the angle. And so I worked through the math, I plugged the numbers in, and it's 18 newtons. Then if I want to look at what force is going to try and counteract friction and pull the book down the table, so it's up here down the table, right? So here's the math. It's a sine function because it is opposite the angle, and I had the other values, and so there's the math. Here's the actual number putting into it. So overall 22 newtons, sine of 35 is going to give us 12.6 newtons down the ramp. So 12.6 down the ramp, and I could go back through and I could label all this if I wanted to. Well, the force of gravity, or the forces acting in the y direction would be gravity down and the normal up, and that's going to be a negative 18 and a positive 18, and they cancel. So net forces are 0. But in the x direction, do they cancel? Actually, they do not. We have gravity in the x pulling down the ramp. We have friction pushing or pulling up the ramp. to counteract? Well, pulling down the ramp, we just determined 12.6 newtons. However, there's 11 newtons in the up direction to the left of the ramp, and so that's negative. You add these two values together, and it turns out, hey, 1.6 newtons is left over. It does not cancel. And so gravity is actually then able to pull the book down the ramp. It will actually slide down this table. The angle is steep enough. We're overcoming friction. And so there is a net force. This book is moving. It is changing its motion. And in fact, as it starts to slide, it'll actually speed up. Because there's a net force acting on it, the book will speed up as it slides down the ramp, or the desk in this case, until it falls off or hits something. Okay, moving on. Okay, equilibrium. We've talked about this, and this is simply when net forces come to zero, equals zero, when everything cancels out, the object doesn't change. You can call this equilibrium, and that's what your book does. So what does this say? When net forces are equal to zero, the object is experiencing either constant velocity or is at rest. The object is then said to be in equilibrium. This is not a term I use as often. I just refer to it as unchanging or some other descriptor. If the object, however, is experiencing a net force, an equal and opposite force is then needed to bring the object back in to equilibrium. So if I wanted to take that book and stop it from sliding down that table, what I would need to do is somehow figure out a way to add an additional 1.6 newtons of external force in the direction of friction up the desk in order to stop that book. Could be my hand, could be something I lay on the book or lay on the desk itself to provide that extra force, but that's what would be needed to bring the book into equilibrium. Okay, so this is just me handwriting where I had the chance to talk a little bit more about that and see what it implies. So let's see what we've got here, because we're almost done. So equilibrium versus non-equilibrium. So anytime net forces equal zero, we know that the object is either at constant velocity, not at CV High School. You're not allowed to be at CV High School. We're in the middle of a COVID-19 epidemic. Please, 6 foot away, people. Get this straight, okay? 6 foot away, wear a mask, wear gloves, okay? Now, in this case, though, the object is either at constant velocity or velocity equals zero, meaning it's unmoving. So it can either be constantly or not moving at all, but there you go. And therefore, it's in equilibrium. So what does this imply? It implies the following conditions. The net force in the x direction, so F sub net x, is equal to the applied plus the friction. Remember, one of these will be negative because it's in the opposite direction, but they are adding together. So force applied plus friction will equal zero in the horizontal. If it equals zero, net force zero, not moving, not changing. Or constant velocity, I mean. And also in the y direction, the forces that are acting in the y direction, the net forces there would be any normal force combined with any force of gravity. Remember again, force of gravity will be negative. So you add these together. If they add up to zero in the vertical direction, there is no net force. So it remains unchanged. So constant velocity or zero velocity. All right, sum of forces equals zero. They all cancel. However, motion will change if any time the net forces are greater than zero. And you can ignore a negative sign here. Remember, negative doesn't mean less than zero. Negative indicates direction. So a negative 46 and 46, same thing to us, except negative 46 is down or negative 46 is to the left. Okay, well, what about the sum of forces in the x direction this time? Well, this is a Greek symbol here. I forget what letter it is. I'd have to look it up. It's an uppercase, but it's going to be sum of. So sum of forces in the x direction for us. So here we have F net in the x direction again. Here is our applied plus our force of friction. But now when we add these together, we're going to get something other than zero. If we do, motion will change. Here in the sum of the forces in the y direction, the net forces in the y will be the normal plus gravity. Remember, gravity again being negative. This will not cancel. This will be zero. This will not be zero. And so if there is a net force in the vertical, then vertical motion will change. When does this happen? Well, throw a ball up, catch it, things like that. Airplanes, elevators, anything that can go up and down, right? Okay, that might just... Actually, I think there's one more slide, so let's go for it. Okay, here we go. Remember about those angles and trig. We already talked briefly about it. Let's talk about it one more time. If the object has forces that are at angles other than 0 and 90 from each other, so something's on a ramp, something's on an inclined plane, we're going to have to use trig in order to resolve those components to make them parallel and perpendicular, so we can then add them together and figure out what cancels and what doesn't. So here I have a simple box sitting on a ramp. I have an angle of some sort. I'm ignoring numbers. I just want to see what's happening here. So I have friction going up the ramp. I have the normal force. I have the force of gravity. And those are the three forces acting on the object. However, I do have components. And so I've drawn them in with a separate color. This force of gravity in the x direction, trying to pull the box down the ramp, could be drawn up here. But then I don't see my triangle. And I like to see my triangle. So that's why I've taken that, and I would actually simply, you could draw it here, then I'd grab it and kind of move it parallel down to see the actual triangle. Whatever this angle is the same angle. So if I want to resolve the horizontal motion up and down the ramp, force of gravity multiplied by the sine of the angle, the way I've oriented this, I'm opposite my angle, so that would be a sine function, and that's going to give me the force of gravity in the x. So what pulls the thing down? Force of gravity times the cosine of the angle will give me the gravitational force that is acting opposite the normal force in the y direction, and this would counter, like I said, the normal force here. So then if we grab this and come down here and we just sum things up. So sum of the forces in the x direction equals the net forces in the x direction, which would equal any force of gravity in this example pulling it down the ramp and friction resisting that pull. Force of gravity can actually be expanded down to here, where the net forces in the x equal force of gravity sine of the angle plus friction. Remember, one of these values will be negative because they're opposites each other. Down here we have the same thing. Oops, I do see a mistake. This should be a y and this should be a y. So please make a mental note of that. I will not be able to fix that with the narration now, I think, because it's going to save as a movie. So anyway, that's permanent, but that's a mistake. Otherwise, everything else looks fine. Force of gravity in the y direction plus the normal force. This expands to actually include the cosine function here. Okay, I think that's it. There will be part 2, which will pick it up literally with section 3 of chapter 4, and it will cover the remainder of that chapter's material, which is also part of unit 4 and 5 of our modeling material. Okay, thank you very much. Hope you took notes, or hope you're going to go back and take some notes. And I encourage you now to read the chapter, which we haven't done a lot of. And I will be deploying some work to allow you to work with this material very, very soon, as early as potentially the following day. Thank you.